In this lab, I want to discuss how to evaluate limits algebraically, but I want to begin by discussing what that even means, or why would we want to be able to do that. Usually the algebraic technique is the one that most students struggle with. So we've seen how to, well, let's start off with a specific example. X squared minus 4 over, let's say, x minus 2, all right? So we've seen how we can evaluate, or at least investigate what's going on with this function. Let's say we want to take the limit as x approaches 2, all right? So clearly, if we just put 2 in, we get 0 over 0, all right, which is undefined, but it's a special case of undefined in the sense that you have this 0 over 0. The numerator goes to 0 and the denominator goes to 0. So the ratio, though, of those might actually converge to a number. If the numerator were to converge to a number and the denominator were to converge or tend to 0, then we would have a case where the function would be going to infinity, or if the numerator were going to a negative number, then maybe to negative infinity. But this right here is called indeterminate. And when we have an indeterminate form, we might be able to transform this function algebraically into one that's continuous at x equals 2. All right. So the idea here is, although we've been able to examine these and investigate what's going on near 2, using graphical methods and numerical methods, right? We could make a table for this. We could draw a graph. Matter of fact, let me go ahead and draw a graph of what this would look like. So we know, well, let's first look at, you might not know right off the bat, but if we were to simplify this algebraically, then it would become pretty obvious. So we see we have a difference of squares in the numerator, so let's rewrite that as x plus 2 times x minus 2. That's how that factors over x minus 2. All right, so this factor of x minus 2 divides, and we are left with x plus 2. So we say that this function, x squared minus 4 over x minus 2, is algebraically equivalent to x plus 2, because algebraically we can transform this function into this one. The important thing here is that these functions are not the same. All right, it's very, actually not hard to see that at all, because if I put in 2 here, I get 4. If I put in 2 here, I get 0 over 0. So clearly at x equals 2, these two functions are not the same. All right, but this function will have a graph that looks very similar to this one. All right, so let's go ahead and graph it. So we know this is going to have a slope of 1 and a y-intercept of 2. All right, so, well, I'm going to come back this way. So something like, well, and I'm going to go ahead right here. Let's see, we're going to go up to 4 over here, right? 2, 4. And this function right here will have a hole right at x equals 2. So it will go something like, this is not looking like a line, but we can fix it, right? Go like this. So there's a line. So let's call that 2. Get rid of that one. We'll call that 1. It's not to scale. It's actually negative 2, right? Negative 1. 1, 2, 1, 2, 3, 4. Okay, so this is a badly drawn line or badly drawn sketch of this, which looks exactly like this right here, except there's a hole at 2. And this is kind of graphically how these two functions that are algebraically equivalent are related. Is the difference is that for this function, this point is filled in. All right? So, I'm trying to really kind of see what's the logic behind doing this, because I don't want this to be just a trick that you just kind of do this factor and you cancel and boom, now I can put 2 in where I couldn't put 2 in before. We need to understand why this works. And the reason why it works, let's call this f of x, All right, this is one function. We'll call this g of x. This is a different function, right? They're very similar. Their only difference is right at the point x equals 2. This one has a hole and this one doesn't, right? So what can we say about the limit as x approaches 2 of f of x and the limit as x approaches 2 of g of x? Well, because this is what we call, remember we call this a removable discontinuity, right? So the limit here, the limit as x approaches 2 of f of x is 4, right? Well, but the limit of this is 4 also, so those are the same. All right. Now I'm just doing that graphically. The whole point of doing this algebraically is because sometimes, you know, the graphical method and the numerical method is somewhat kind of guesswork, right? We're just trying, we have to base it on the best graph that we can get. Or numerically, we can make a table of values, but ultimately what happens, we can only get so close, right? We can keep on getting closer and closer and closer, but we could go on forever trying to pick values closer and closer to 2 to see what's happening here. So in a sense, we're basically having to look at the graphical or the numerical evidence and then basically make a guess as to what the limit is. All right, this method gives us basically kind of a proof that indeed this limit is 4. All right, so the key is that this limit, let me just to highlight this, I'm using another color, this limit and this limit are equal. All right, that should be kind of obvious here. The difference is this g of x is a continuous function. So we know that because it's continuous, we know that the limit as x approaches 2 of g of x is just g of 2. Right? That's what continuity, remember, quick refresher on continuity, the limit as x approaches a of f of x is f of a, or in this case g. So if so we have the limit as x approaches 2 of g of x is g of 2. That didn't work here because f of 2 is undefined. That's what we found here. So this is kind of the logic, is that this function has the same limit as this function, and this function is continuous. So if we just transform this function into this one, we can use the continuity of this function in order to find this limit, right? Because g of 2 equals the limit of g of x as x approaches 2, and this equals this. So that's the basic idea. I think it's important that you understand why this works and what the motivation is for doing it to begin with, as opposed to just saying, well, here's a bunch of techniques for simplifying, and that's what I'll do in the next video, is I'll show you some techniques. How do we, this is one way. So this is, I should just kind of let me put a label on this technique. We factored, all right? So if we can factor the numerator, in this case, factor it, and then we can cancel out the term that's causing problems, right? This x minus 2 is what's causing the issue here. We can cancel that or divide it. Canceling is not really a mathematical operation, right? But it leaves us with something that's continuous at x equals 2, but algebraically equivalent to our original function. And so that's the easy way to evaluate it. In the next video, I will give you some examples of different. So we have factoring. There are, a handful of techniques that we could use that would help us transform functions that are not continuous at a point into functions that are, and then use the continuity of that function in order to find the limit of this one.